Welcome back to Codex. Next up, we have another talk that was rescheduled from the 2022 JMM special session on recent advances in packing. Our speaker is Dustin Mixon, who is an associate professor in the math department at Ohio State. Professor Mixon studies applied harmonic analysis and mathematical data science. Today, he will tell us about an approximate Positivstellensatz. Take it away, Dustin.
Great, can you hear me okay? All right, so I'm going to be talking to you about an approximate Positivstellensatz. This is joint work with Hans Parshall. The motivation is a problem that I think many of you are aware of. We're interested in this problem of we're given a couple numbers, D and N. D is a dimension of a vector space, a real vector space. N is going to be a number of lines going through the origin of that vector space. We're interested in finding N points in this projective space, this real projective space, that has the property that we maximize the minimum distance. So if I were Joey, I would talk about kids in the back seat of a car and trying to keep those kids separated so they don't swat each other or whatever. But I'm not going to tell you that story. Okay, I want to share with you some things that we know about this problem. These are small dimensional cases. So the way to read this table is these numbers are dimensions, and these numbers are numbers of lines through the origin, okay? And so if you start thinking about this problem, maybe the first thing you're thinking about is how do I arrange n lines through the origin of R2, okay? And it's not too difficult to convince yourself that the best way to do it if I have two lines is to make them perpendicular to each other. If I have three lines, I'm going to have them go through antipodal vertices of a hexagon. In general, you're going to uniformly distribute your lines, and you can prove that that's optimal by some sort of pigeonhole argument. So all of these can be proved using a pigeonhole argument. If you want to do higher dimensions, you'll have your lines be spanned by unit vectors. And if you have at most as many lines as you have the dimension of the space, then you can get away with just having orthonormal vectors. So it's really easy. Things get more interesting when you have more vectors, more lines than the dimension of the space. Some classical bounds that much of the audience is aware of is the Welch Bound, and you can get Welch Bound equality whenever n is d+1. You get this by taking the vertices of a regular simplex. Think of the center of that simplex as the origin, and then make lines go through the origin and each vertex of the simplex. That'll give you a system of lines that achieve equality in something known as the Welch Bound. There's a few other instances of Welch Bound equality on this little table. If you, there's a similar bound known as the Orthoplex Bound. You can achieve equality in that bound in a few places. And otherwise, you have to like be a little scrappy with your math. I guess I should mention there's a Boot-Cox bound, which you might think of as being in the tradition of Welch and Orthoplex. But otherwise, we see some cases here that are a little more scrappy. You'll see we'll actually focus on these last two, these yellow cases. So MP2 because it's me and Parshall, and it's the second of those papers that are represented here. Okay, M stands for me. Okay, how are we going to go? So we're going to represent our lines with unit vectors. Say V1 through Vn, all sitting in RD. Okay, and once I have those things, I will think about, the whole talk is going to be thinking in terms of a gram matrix. So the gram matrix we'll denote by G. This is going to be an n by n matrix where the ij entry is the inner product between Vi and Vj. Okay. We're trying to solve an optimization problem over all possible gram matrices that come from this process. So let's denote the feasibility region. This is the rank constrained elliptope, if you want to sound fancy. This is the set of all n by n matrices that are symmetric. They're going to be positive semidefinite. They're going to have rank at most D. And they're going to be all ones on the diagonal. Okay, that's the set that we're going to be optimizing over. And the thing that we're trying to optimize, the thing that we want, once you pass to these gram matrices, we want to minimize a thing over all possible gram matrices. We want to minimize the following quantity. Some people call it the coherence. It's going to be the maximum absolute off diagonal entry. Okay, that's what winning looks like, is minimizing this quantity. Questions so far? Okay. The observation that makes Positivstellensatz relevant is the following. So we're looking to minimize this quantity. Consider the following set. So take all G in this rank constrained polytope that has the property that the thing you're trying to minimize, this coherence thing, is at most mu. Okay, so the set of all gram matrices for which this objective function is less than or equal to mu. Suppose this were empty, this set, this preimage. Okay, that would imply that the value, the thing that we're trying to make as small as possible, this minimum here, is going to be something in terms of mu. See if you can figure it out before I write it. Okay, so if this sublevel set is empty, that means there is no G for which this number is less than or equal to mu. So the smallest you could possibly be must be strictly bigger than mu. Okay, so if we could figure out how to determine whether certain sets like this are empty, then we can conclude lower bounds on this thing that we're trying to minimize. Okay, so it begs the question, how do I certify that a set is empty? It's really easy to certify that a set is non-empty. You just provide a witness, provide a member of the set. But showing that a set is empty, it's a lot harder in general. I want to point to you to an example that's particularly illustrative on how you might actually accomplish this in our case. So consider the set of all real numbers x, for which x squared plus 2x plus 2 equals 0. Okay. You might want to convince somebody that this is the empty set, but then how would you do that? Maybe you would think of drawing a graph or something and showing that a certain parabola doesn't intersect the horizontal axis, something like this. There's an algebraic way of accomplishing this called completing the square. And I'm going to accomplish this in a suggestive way for later. So I can look at the square of x plus 1 and then I'll subtract the quantity that needs to equal 0. And when I do that, this guy is x squared plus 2x plus 1. I'm subtracting the same thing, but bigger by 1, so I end up with -1. Okay, so let's use this identity to prove that S, my original set, is empty. Suppose, for the sake of argument, that there's some point in S. And let's see what happens. So I got some X in S. I plug that in to here, I get a non-negative number. And I plug that into here, and by definition of S, I'm getting 0. So the left-hand side is non-negative. Meanwhile, by the identity, the left-hand side equals the right-hand side, which is -1. Okay, so I obtained a contradiction. If there's an X in S, then math doesn't make sense. So it must be the case that S is empty. Okay. So this is a way of certifying. Somehow this identity certifies that S is the empty set. Okay. And this generalizes this trick. Let's talk about more general stuff. So let's say S is a set of all X in Rn, for which I got some polynomials, call them Fi. I want these polynomials to be non-negative for every I in this finite index set. And I want Gj to be exactly equal to 0 for all j in this other finite index set. Okay. This is a generalization of this setting. And we're going to identify a generalization of completing the square. In order to do that, I need to introduce some stuff. Let's talk about the cone. The cone is going to be determined by my F polynomials. This is going to be the set of all sum of squares combinations of products of the Fi's. So what I mean by that is you look at all possible ways of multiplying the Fi's together, okay? And then you linearly combine them where the scalars are squares, or in fact, sums of squares of polynomials, okay? We're also going to talk about an ideal of sorts. This is the ideal generated by the GJs. These are polynomial combinations of those GJs. Okay, so let's use the cone and the ideal in order to certify the optimality of S. Or rather, certify the emptiness of S. So we're going to say, suppose we have a polynomial in the cone and another polynomial in the ideal with the property that P of X plus Q of X is -1, okay? Suppose I had an X in S, okay? Then that would mean that plugging in X into this thing, I have a sum of squares combination of products of these Fi's. And I know since X is in S, all of those Fi's are non-negative. So then these sum of squares combinations of those non-negative things must also be non-negative. Furthermore, when I plug X into Q, Q is in this polynomial combination of things that vanish on S. So that must be 0. So overall, this left-hand side is non-negative. It's the same argument as we had before, where we had something that's non-negative on S and something that vanishes on S. Okay, the left-hand side equals the right-hand side, which is strictly negative. So there's my contradiction. That must mean that S is the empty set. So this can be summarized in something called Stengle's Positivstellensatz. which says that the following are equivalent. The thing that you care about, namely S is the empty set, and then this certificate thing, the fact that -1 is in the sum of the cone and the ideal. What I just walked you through here is the proof that if -1 is in the cone plus ideal, then you have a proof that S is empty. The amazing thing is that if S is empty, there's necessarily a certificate of this form that gives it to you. I should say S necessarily, for all this to work, S needs to take this particular form where these F's and G's are polynomials, real polynomials, and there's finitely many of them. Okay. All right. So let's talk about how to interact with Stengle's Positivstellensatz in practice. So it turns out that you can access sum of squares certificates using semidefinite programming. You do a certain lifting move and observe that a matrix is a Gram matrix. I don't know if you've interacted with semidefinite programming before, but it's pretty slow, frustratingly so. So for our particular application, namely showing that, like trying to prove a bound like this, we actually break the problem up into a bunch of little sub-problems using something called the contact graph. And here we're ending up with thousands of contact graphs to case over. This reduces the number of variables that we have to fight with. For each of these thousands of cases, we run our SDP solver on the corresponding sum of squares instant and obtain a certificate. What it gives us is a P in the cone and a Q in the ideal, such that P plus Q plus 1 is approximately 0 coefficient-wise. Okay, and so now you look back at this Positivstellensatz and you realize, wait, this thing does not say -1 is approximately in the cone plus ideal. So can I conclude this? And that's where the approximate Positivstellensatz comes in. So you don't get something for free. You have to start with you get a stronger hypothesis, and then you get to conclude the thing that you want. So suppose S, this thing that you want to show is empty. Suppose you're able to show that it's a subset of the infinity ball of radius r. Okay. It's not easy to, or excuse me, it's not hard to do that in practice. For example, in our case, I'll show you that in a second. So suppose that happens, then the following are equivalent. The thing you want, namely S, is the empty set. And then the thing you can show, namely there's a P in the cone, there's a Q in the ideal, such that the max absolute value coefficient of P plus Q plus 1 is at most a number you can compute. I'll just write it out to prove the point. Okay. So the way you use this is you run your semi-definite program to identify P and Q. You take the sum, you look at the coefficients, and you ask, hey, are those absolute values always less than this number? If so, you're done. You've established that S is empty. So going back to our case, whenever you have S being a subset of our rank constrained elliptope, you can take R to be 1. The biggest entry of your Gram matrix is going to be at most 1 because it's unit vectors. Cool. And then at the moment, there's a gap between what I promised and what I'm giving you. Here, I'm giving you a technique for showing strict inequality, okay? But I'm claiming here that we have characterized exactly what the optimizers are, okay? Turns out there's a second routine you have to run. This prunes all of the suboptimal contact graphs. For the optimal contact graphs, you have to run a different thing called cylindrical algebraic decomposition. All right, that's my time. Thank you.
All right, thanks, Dustin. And let's see, maybe I should ask Dustin actually to hit the button, as he normally does, to stop the recording.